Okay, so now we're back. And now what? Well, instead of saying that this bottom left part is finished, we could say, well, what if we've not yet figured that one out, but we have computed the top right part of U? Okay? In that case, we don't need this, because we don't need to know how L bottom left is related to everything else. Instead, what we need is this is equal to that. L top left times U top right is equal to A top right hat. All right? Now, what's the natural next step? Well, we could say U top right has already been computed and L bottom left has already been computed. And if we do that, we need to throw back in that L bottom left times U top left is equal to A bottom left hat. So now this is loop invariant number 4. How do we come up with loop invariant number 5? Well, we've used that this is equal to that. We've used that this is equal to that. We've used that this is equal to that. We haven't yet used that this is equal to that. Now, we could say that L and U bottom right have been computed and have overwritten A bottom right. Well, wait a minute. That means that we're completely finished with our computation. That doesn't make any sense. So, what we do instead is we go and we look at this right here. Now notice that that's L bottom left, U top right, plus L bottom right, U bottom right, is equal to A bottom right hat. Now, if we've already computed U top right and L bottom left, then we know this term right here. So we could go one step further and say, let's take that and let's subtract it off of the right hand side. This minus is a little hard to see. And we know that in the end then, we need to compute the LU factorization of that. Now, we don't want to go all the way and compute that, but we can say a partial result towards that is to also go and update the bottom right part of A by subtracting off that right there. And how would we capture that in our loop invariant? We would say A bottom right has been overwritten with its original contents with L bottom left times U top right subtracted off. And notice that we don't need a constraint right here, because everything you need to figure out what L and U top left, L bottom left and U top right are is all captured by these constraints right here. And now we have 5 different loop invariants from which we can derive 5 different unblocked algorithms, and then ultimately we can derive 5 blocked algorithms. Okay. Now here's something interesting. A book written by G.W. Stewart, also known as Pete Stewart, on its cover has the following. Okay. And what do you notice? If you look carefully at these pictures, you will recognize the different loop invariants. Now, he describes these different algorithms, but he doesn't describe a systematic derivation of the different algorithms. That we're doing right here.